All right, so welcome everyone. Welcome to this Scikit-image tutorial, and we're looking forward to spending the next few hours with you, telling you a little bit about this this package. I'm not sure what field you guys are in, but like images tend to crop up all over the place in science, and it's a very rich modality of measurement, and you see all sorts of different kinds of measurements, whether you're looking at neuroimaging data or satellite data or microscopy data, very different kinds of data, but bound together by the fact that they're all essentially images. So in a sense, Scikit-image has got a fairly wide reach, but it's also quite specific. So in this tutorial, we're going to be teaching you how to use Scikit-image and apply it to images represented as NumPy arrays. So NumPy arrays will be the fundamental unit of exchange between not only Scikit-image, but all the other libraries in the scientific Python ecosystem. So all of these packages are kind of loosely tied together. SciPy used to be the big monolithic package that included all the different parts of scientific processing. But as packaging improved across the ecosystem, we were able to sort of create these smaller projects, factor out these smaller projects. And you may be aware of a few other scikits, like there's scikit-learn, there's scikit-image, and I actually included a link here in the notebook. Let's see. So there's a site out there called AT&T Wi-Fi. Okay, that's not what we want. So there's a site, scikits.appspot.com, and if you go to download a scikit, you will see that there is a fairly long list of packages by now, all bound together by this scikit. It's not a namespace, but it's like this common naming convention. And all these packages are built on top of NumPy, so most of them exchange their data as a NumPy array. So everything you learn today will be applicable to all the other packages in the scientific Python ecosystem. Right, so you got the installation instructions, so I'm not going to go into too much detail on that. If you have Scikit-image running, you should be fine. The example images we'll be using today are either included in this repository, and if you haven't refreshed this repository recently, I suggest you just do a clone, or if you got it directly from GitHub, just download the latest zip, because we made a few additions still over the last few days. So, last few hours, yes. So this is a rough overview of. Say again? Okay, so yeah, let me get to that then. So if you downloaded the repository, which you can find. So if you go to github.com/scikit-image/skimage-tutorials, that's the repository that you need for the tutorial today. So you can either click on, there's a download as a zip file icon, there, clone or download. You click that button and you have the option to either download the repository as a zip file, or you can use this URL and clone it with Git if you feel comfortable with that way of getting it. And this is mentioned in the installation instructions too. Right, so what we're going to do is we're going to fire up the Jupyter notebook from the root of that repository. So just unpack all those files and launch Jupyter from the root. So you should see there should be a README file and an index.ipynb. Just do, I think, Jupyter notebook is the way to launch it. So that should open up your browser, and you should see something like this. Okay, so we're going to be working from the 2016 SciPy tutorial. So click on that folder and click on the index file. Right, so if you get to this point, you're ready to follow along. So let's have a look at the schedule for today. So Juan is going to start by telling you a little bit about how we represent images in Scikit-image. So how do we use NumPy arrays to represent images? After a short break, we'll continue on to image filters. So how do you modify, clean up, etc. images? He'll then proceed to tell you about segmentation. So how do you identify objects inside an image? After a slightly longer break, I will illustrate the ransack algorithm to you and how that works and how you can apply it to image processing problems. And finally, we're going to be looking a little bit at geometric transformation and warping. So how do you take images and sort of project them, change their shape, pull them in different directions. And as an application of that, I will show you panorama stitching as well. So how do we take several images that overlap slightly and add them all together? Okay, so just to round off the introduction, I'd like to show you some real-world examples of Scikit-image out there. So here's an example of radiometric dating done by Alexandre Fioravante de Sequeira. Here's some work done by Emmanuel Juillar in materials science, doing tomography of materials and then segmenting the structure of the material out. The GammaPy project, they're generating this source catalog from their images, and part of that processing pipeline is based in Scikit-image. 3 medical applications. At the top, Nadav Horish's company, VisionSense, they use Scikit-image to work with endoscopic surgery images. Work I did with Francha Milan in South Africa, where we used Scikit-image to align images of fluoroscopy images of hips in the process of being refixated. And then finally, a fairly recent addition, a 3-dimensional skeletonization example by Beta Krakel's clinical graphics company. Here's some quantitative histology done at Princeton's Department of Ecology and Evolutionary Biology by Quentin Cordron and his colleagues. And finally, a satellite imaging example from Robin Wilson in the UK. Just to give you a flavor of the kinds of things that are happening out there. All right, so I think without further ado, there are some other issues I'm happy to discuss afterwards. Like, we often get questions like, what's the difference between ND image and Scikit-image? And briefly, I'll just say that Scikit-image essentially builds on top of SciPy's ND image. And then the Scikit-image versus OpenCV issue. If you're doing real-time image processing, at the moment, OpenCV is what you want to be using. We don't have SSE2 optimized code that's hand-tuned. We're looking at solutions in that direction, and we've got various plans for looking at that. But as of now, the strong suite of Scikit-image is that you've got good documentation, you've got a Pythonic API, and you've got a user community that contributes and supports you. Okay, so without further ado, I'll give over to Juan, and he can tell you a bit about how images are represented in NumPy.
Can you show me how to get to your terminal?
You want to get to a terminal?
Yeah.
So you hold the Windows button and click. I'll open up. Okay, so Windows button that way and this way.
All right.
And let's make it a bit bigger. You want IPython?
No, I don't. I want to set Vorak, which people shouldn't see.
Okay, you want to be in the directory of the...
No. I'm just setting Vorak layout.
Oh, I see. I see. Okay.
All right, nobody do this. This is just my weird keyboard layout. Because my... All right, we're good. Are you a Vorak user? Awesome.
This is something else. Just
No, because I normally would, but since he has to teach you guys later, then I won't do that to you guys. All right. So why don't you go ahead and click on the first tutorial, images or NumPy arrays. And that should open up a new tab with the tutorial.
And if this doesn't work for you, just put up your hand and I will swing by and give you some assistance.
Yeah. Okay, so the first thing we're going to do, if you're not familiar with the notebook, you want the images to display inside of the notebook. You do this with this magic command, %map.lib inline. So if you press Shift-Enter, that should run that. And that's completely unnecessary, but we'll do it. Okay. So the first thing we're going to do is generate a random NumPy array and show how you can just interpret that as an image. So if you import NumPy as NP, and then you import map.lib, numpy.random generates random numbers. So this gives you a 500 by 500 NumPy array of random numbers, and then you can just use map.lib's imshow to display those. Okay?
Fine.
Yes?
Sorry to stop you, but I thought we could just hand out the notes quickly.
Oh yeah, go for it.
So if you could take a green, a yellow, and a red or purple, pink or purple sticky, we'll use those as status indicators to see if you're following along or not. So just grab 3 different color sticky notes.
All right, so those will be passed around. So as you can see, you just get an image of gray noise, which is basically what you would expect. And you can just use the same command for real-world images. So Scikit-image ships with a bunch of example data. You just do from sk-image import data, and then there's a bunch of functions there that you can explore later, but we have a coins image. And if we run this, you can see that we've got a NumPy array. The data inside of the NumPy array is unsigned integers, 8-bit, and it's 303 pixels by 384 pixels image. And that's the image, again, using the imshow command. Okay. For a color array, you do the exact same thing, but then there's an extra dimension on the array of size 3, so that you've got red, green, and blue channels on it. So this is cat image. That's one of our example photos. And then you can see that it's got 300 by 451 pixels and 3 channels. Okay, and again, map.lib's plt.imshow will just show you the image. Feel free to interrupt with questions at any time, by the way. Okay. So the thing that we want to drive home in this lecture is that these really are just standard NumPy arrays. There's nothing special about these objects, and that means that you can do standard NumPy operations on these images and process them how you want. So if I want to set the pixels between 10 and 110, and in the square that's given by 10 and 110, and 10 to 110 on the x and y coordinates, to red, then I just pass it the red, green, and blue channels, and assign that, and now we can see that I've added a red square. Okay? So the fact that these are just NumPy arrays makes it very easy to process your data however you see fit, and write your own functions however you see fit. So we'll do a quick aside about image values. So everything that we've done so far has been, as you can see, you can't see it here, but let's just edit. plt dot, no, oh, sorry. So if we do type, no, cat.dtype, what is happening? Print cat.dtype. You see that it's a uint8 array, okay? And it's got values between 0 and 231. The maximum value would, of course, be 255. Okay, so Scikit-image will recognize a bunch of data types as images. The 2 most common are these uint8 that we just saw, where you've got 0 is black and 255 is white. But we also often work on floating point images where 0 is black and 1 is white. And obviously floating point images have huge floating point numbers can represent a huge range of values, so we use 0, 1 as a convention. So let's show these two kinds of images here. So if I do linspace, this gives me evenly spaced values, numpy.linspace, evenly spaced values between 0 and 1. And then we should reshape that into a 50 by 50 array. And then we do the exact same thing, but between 0 and 255. And then we cast the type to uint8. And you'll see that you get exactly the same image displayed. Okay? So as I said, these are two valid ways of looking at the same data. And you'll use one or the other depending on what's more convenient at the time. We often do float because then when you're doing a lot of arithmetic operations on the arrays, you don't lose precision to rounding and overflow and underflow effects. So Scikit-image, one of the most common things to use is these utility functions that will do the range and type conversion at once for you. Yes?
Sorry, I just wanted to ask about the floating point. Does all that apply to color as well as?
Yes. Yes. So if you have RGB, then each of those channels should be in 0, 1. Yeah. Yes, which you will see right now. So because we're converting both range and type, it's often convenient to have a function that does both at once. And so Scikit-image provides images float, images ubyte. Ubyte is another way to call uint8. And so if we have an image, then we can convert it to both types and print them out. And display them. Print them out. Okay, so if we've done images float of that image, then you see that the values are between 0 and 0.9058, so on. Or if we do images as ubyte, they're between 0 and 231 as before. And you can see that all it's doing is dividing by 255. So 231 divided by 255 gives you that same value as above. All right? Okay. So as I said, we usually recommend doing floating point because a lot of operations will do interpolation, things like that, which you don't want to get rounding artifacts after pipelining lots of operations one after the other. Okay. So we're going to do a quick aside that we'll be able to stop doing once matplotlib hits 2.0, which is about color maps. Okay, so we've already done a bit of displaying of images, but you might have noticed in all of our display calls we specify cmap equals gray. So that's saying how do I convert from integer values to what I see on the page, and you can map to a whole bunch of different colors, or you can map to a grayscale level. And so by default, until soon, matplotlib uses one pull request. All right. Well, so one pull request and then beta and then RC. Okay. All right. Cool. Yeah. So you've all got stickers now, which is great. If you need help, you put up a red sticker. And then later when you're doing exercises, we'll use green for finished, yellow for working but fine, and red for something's broken, I need help. Okay? Blue means green, yes, sorry. Or green means blue. All right. The good color. Okay, so by default, until soon, matplotlib will show images using this jet color map, which is a holdout of long history of matplotlib. And jet has a lot of properties that you don't want when you're displaying images, which we don't have time to get into.
Sorry, the screen is very dim. What?
Oh, because it's work.
Type brightness 1 and type enter.
Brightness 1?
Yes.
All right.
I was like, what?
All right. So things are now brighter, apparently. Okay, so is this working now? Did you break your keyboard again?
I think so.
Well, yeah, it's not functioning. Go do it.
There's a Linux kernel bug, so for all the good display goodness we get, we don't have a working keyboard, so. Oh God, okay. There you go.
Oh, well done. All right. So, I'm just going to zoom in to the part of the face to illustrate the jet's distortions. So essentially, you can just look at this guy's face, and you can see that the face is all splotchy, and there's kind of contours around the dark and light areas, which are just smooth transitions in the grayscale. Okay, so this is a nice intuitive example of why you don't want to use jet. And so we will not be using it for the rest of the tutorial. I'll do one more artificial example. So here you've got a smoothly varying signal from the center to the outside, and in jet you can see contours kind of all along the way because of the way that it maps intensity to color. So yeah, basically you don't want to do that. So what we're going to do is we're going to set as default grayscale as the color map, and you can do that through the RC params, which is your default parameters for map.lib functions. And so for the color map for images, we're going to choose gray. And for interpolation, because we don't want, we want to see kind of the value at every pixel, we're just going to use nearest neighbor interpolation. And I'll skip that bit. Yes, so the current version is 1.5 point something, but 2.0 will be coming out soon. It will be Veridis. All right, I will show Veridis. It'll be this green thing. So this green thing has higher perceptual delta, so you can display more values than gray, but it also has uniformly varying intensity and color. And Magma is another one of the new color maps which you can use, but won't be the default, and that's this one. So use whichever one looks prettier to you.
And the projectors, even in those examples, you see a little bit of ringing, but that's due to the projectors not being very good.
Yeah. Okay. I'm going to skip the interpolation demo. Okay, if usually you won't want to be working with Scikit-image's provided images, even though it's cool to have that resource for these demos. So if you want to read images into NumPy arrays, Scikit-image provides this I/O module. So from Scikit-image import I/O, and now you can just do imread to read files. Okay, so that's a JPEG file that lives on disk, and you just read it with the imread command. There's also an imread collection, which will give you a collection of images in a iterable object. Okay, so if we run this, and the nice thing about the image collection is that by default, I think, it doesn't load up all of the images at once. It only loads them up as you request them. So right now, it's got a bunch of image files that it's got pointers to, and if you just want to show one of those, let me do that. plt.imshow. IC of -1. Is that going to work? Yes. Why does that look so funny? Let's look at the range of that thing. Oh, what did I do? I should not have done that. Yeah, that's interesting. Okay. No, what am I forgetting? Comma. Okay, so I don't know why that image looks so terrible.
Do you see the same result, or is yours fine?
All right, great. So we're going to blame Stefan for that one. Okay, and so you can basically iterate over all of these images and display them. And hopefully most of them will look better than that. Yeah, they do. Okay, so if you have a collection of images that you want to process, you can use imread collection to load them up all at once, the same way that you would load them up on the terminal using star notation and so on. Okay, so now we're going to do an exercise which will be just like drawing the square, but with a slightly more complicated shape. So the idea is if you want to code up a function that will take an RGB image as input and a pair of coordinates, and it will just put a little h on that using standard NumPy functions. So you have two options when you're reading in an image. You can either modify it. If you get a NumPy array, you get a pointer to that NumPy array, right? So if you modify that array, then the array will be modified even in the outer scope. So if you don't want to do it in place, which is often a good thing. The idea is, so you're going to modify this function. So you can deal with in place however you would like to deal with it. Okay?
So that's one of the big advantages of NumPy over something like matplotlib is like it's so MATLAB. It's so easy to modify one value in an array in MATLAB, and then a whole copy gets made of that array. I imagine you work with really large images. You modify the array, and all of a sudden you put two images in memory, and then So NumPy by default, when you modify the array in memory, it just changes that array, and all the variables pointing to that array will also change. I mean, they're all pointing to the same thing. So if you make a copy, it takes that data, it explicitly makes a new array for you, and you can go and modify that array.
Okay. So yeah, so use your stickies. So everyone's yellow stickies can go up. Sorry? Oh, if your coordinates go outside the images, oh, sorry, minus 50. So NumPy allows negative indexing, which means from the border. Yeah. And if you just pass that kind of coordinate to NumPy, it'll know what to do with it. So that's fine. Yes. So don't go outside the image. NumPy will wrap around for you, so that's fine. All right. I'm just going to quickly go over the first solution. So essentially all we're doing, so for the in place, you just copy it if someone doesn't want it in place. Then you're just going from the top row to the top row plus the height, and you're going from the starting column, and then you're adding the thickness. So that's drawing your rectangle, which is your first bar of your H. You use integer division to get the location of the height of the strut. And then you add the thickness of the strut. And in the other dimension, you just go from the left end to the right end, which is just adding the width. And you can do the same thing for the final strut. Okay. And so just by doing array indexing, we can draw on an image. That's the gist of that exercise.
Did you run it?
Yeah, so if I run it and I put it at 50 minus 50, there's your H.
Make it red or something?
Yes, I can make it red. Okay, maybe I can't make it red. Oh, because yes. No, that should be... Oh, right, sorry. Okay, so we've been talking about image types. My image is uint8, and I'm giving it a value of 1. Or if I'm assigning a value of 0.8, it's just going to truncate that to integers, which is why it's black.
This image, the values are running between 0 and
255.
255.
Yes. So when I give it a 1, 0, 0, slightly red, but you can't see it, right? So if I try...
Isn't there a way to make sure when the image comes in that it's always
There is such a way. This totally is not rehearsed, by the way. It really isn't. Okay. So I mentioned earlier utilities to convert. And the nice thing about the conversion, so if I do an image as float, is that if it's already a float, it's not going to fail. It's just going to give me my float image back.
Is that going to make a copy, though?
It's going to make a copy, which will make the in-place thing, yes, you're completely right. So if we had time and inclination, we would say we can't do an in-place while converting the values. But we don't have either of those things. All right, so I can just do out equals image as float of out. Okay? And so that's going to make a copy regardless, which means all the other stuff is irrelevant, but now I can do this.
So that always converts image to one that is 0, 1?
Yes. All right. So this makes sense, and if I want yellow, then I just do that. Okay? Yes?
Can you explain the coordinates? You said it should be at 50, -50, but it's not according to the axes.
What makes you say that? So it's negative 50. So NumPy and Python, negative coordinates means start from the end. So this corner here, the top left corner of the edge, is 50 away from the right edge.
Why print the...
But why second variable?
Sorry, what?
I would expect that comes to 50 is x coordinate.
Yeah. So Stefan briefly touched on this. NumPy indexing works like matrices. So that means top left is 0, 0. The first coordinate is the rows, and the second coordinate is the columns.
What did you change to make it possible to draw yellow edges?
So it's what I assign. So yellow, I just give it a different color value. And here, when I give these two coordinates, coordinate ranges to color, I get back an array that is a rectangle by 3. And if I assign a value of 3, then it'll repeat that value of 3 for every single one of those coordinates.
Initially, it was just black page.
Yeah. So black I would do by doing 0, 0, right?
I think part of this lecture is to realize that images are just NumPy arrays. They're the same thing. So you're actually working with matrices. So that's why the indexing is not surprising. Because that's the way you're indexing to a matrix, right? The matrix and image, you should see them as exactly the same thing.
Yeah, so the indexing definitely becomes second nature, and if you're in scientific Python, you use NumPy arrays all the time. And so certainly, if you find it surprising now, spend a little bit of time with NumPy, and you won't find it surprising at all. Okay, so did that answer your question about the -50? Is that? Yeah. Yeah, sure. So this is because we're doing NumPy indexing, and NumPy indexing works. So I can change this to.
It's Python, right?
Yes, you're right. It is Python. So in Python as well, if you index into a list, minus means start from the end. All right. So I'm just going to start typing on this stuff. If you're not finished with exercises, keep going. Actually, you can keep going or you can take a 10-minute break because we're about at that point. And I'll just show the solutions briefly after you come back. So 2:30, we start up again. I'm just quickly, hopefully, going to go over the solutions to the other thing, to the previous exercise. Yep, so everything's been saved, which is good, but the kernel will be new, which means we'll need to run everything again up till here. Okay, so I'll leave this here for the cell all above. Okay, So that's the solution to draw H, which we saw briefly before the end. All of the solutions will be posted after the tutorial. So you don't have to worry about that if you don't catch this. But essentially, we are just indexing into the NumPy array and assigning to the color value that we gave it. Okay, so why is that not working? Keyboard's frozen again. What? No, the keyboard's frozen. I need my keyboard back.
There you go. Just that shift in R reloads the.
All right, great. So that's drawing the H. So for plotting the intensity, exercise number 2, all we need to do is grab the given row, grab all the columns, and grab the corresponding color. Okay, so 0 channel. So this is, again, standard NumPy indexing. Each of these will now be a one-dimensional array, and we can just use plt.plot. And I think we're probably plotting them in the wrong order, but nevertheless, let's just here. To do it correctly, you probably want to do specify the color. G. Okay, so that's the call. And then here I've added a few extra calls than the ones you have just to show where we're plotting, which will make what we're doing easier to see, okay? So this is the 50th line cutting across the cat. And so you can see right where you hit the cat's ear, the intensity goes down. It's a bit wider here. It's a bit darker here, and so on. Same at the other end. And if you go to the 100th row, then you can clearly see where the eye intersects the line as a big dip in brightness, right? So again, the fact that your images are just NumPy arrays lets you use a whole bunch of stuff from scientific Python. The last one is just a little bit of a Python 3 showing off. If you don't have Python 3, you would replace this with cat dot dot, and it's a function. But in Python 3, you have this new matrix multiplication operator. And so what you're doing to get the luminance based on this formula is you're multiplying the red, green, and blue values by these coefficients, and then you're summing them together. And that's the same as the dot product. So you can use the matrix multiplication from Python 3 and just get the last dimension of cat multiplied with this array, and you get this thing.
That human eye is more sensitive to green than it is to either red and even less to blue. So you have to weigh the channels differently when you convert to gray because that's just the physiology of it.
Yeah. Okay. So let's go back to your index and go to image filters. And this will go a lot quicker because we got to get through 2 sections in limited time. All right, so we'll do this matplotlib inline just to show the plots in the NumPy notebook, in the Jupyter notebook. So let's talk about, oh, sorry, let's do one more thing, which is set the color map to gray and turn off interpolation, okay? So local filtering refers to replacing any value in an image with a value that's a function of its neighborhood, okay? And what we're going to do is we're going to show how this works with a one-dimensional signal, and then you can generalize to 2 dimensions or higher. So here's our signal. Okay, it's just a step signal like that. If we add some noise to it, right now it's very clear what's going on, right? If we add some noise, it'll be a little less clear, okay? So there's the low values and then the high values there. If you want to smooth the signal, one of the easiest ways of doing it, if Stefan hadn't not pulled, is to take the neighboring values. So you take the value at that pixel and its 2 neighbors, and then you take the average, okay? So doing this in NumPy looks like this. You're just going from the 2 pixels in, and you're going to 2 pixels out, and then you're shifting the array on top of each other, summing it, and dividing by 3. Okay, and so you get something that's of the same range as before, but slightly smoother. Still not very smooth. All right. That's not even right, is it?
Why did you change the 1 to 2?
Because I wanted to, this is what I actually want to do. So I just want a centered filter, if that means something to anyone. So let's make this into multi-line so we see what's going on. So we're summing 3 signals slightly shifted from each other, and then dividing by 3. That's the, yeah. Okay, yeah. So now you've got things around 10, which is where we started, and it's smoother. Okay. So this exact operation can be expressed using what's called a convolution. And the idea is we're going to take something called a kernel, which can also be called a structuring element or a footprint, which is just 1/3, 1/3, 1/3. Okay, so an array of 1s divided by 3. And what we're doing is we're going to translate this kernel over our whole image and take the center pixel, and we're going to do a summation, sorry, a multiplication and then a summation, kind of like a dot product. And then we're going to replace the value at that pixel with the result of that. So it's exactly what we've done, but instead of doing this mess of averaging and indexing, we just do a call to numpy.convolve. Okay? So let's try to port that to an image. I'm going to make one of the simplest images possible, which is just a little square like this. All right, so that's just 0 out here and 1 here. This is nice because it's easy to reason about 0s and 1s, and we'll see what's going on. Okay, so in 2 dimensions, instead of 3 values, you've got 3 by 3, a 3 by 3 square, and so you divide by 9. So we do 1/9 times numpy.ones of 3 by 3. So that's our main kernel. And then we can just do the same thing as above with convolution. So the same way that we were smoothing 3 neighboring values in 1 dimension, we are now smoothing 9 values in 2D.
So that's not, I mean, that's happening on the original data each time, right? So it's not.
Yes, that's right. So there's whenever you take the mean of the values, you're taking it on the original image. You're not sort of replacing it in line as you go, which would be weird, I think, mostly. Maybe not. I need to think about that one. Okay. So Tony Yu, who is not here right now, wrote this very complicated function that I'm not going to go through. But the gist of it is that you can actually show this operation step by step. Okay, so up here we're representing our filter. The values around the array are taken to be 0, and then we just go step by step. Okay, so every time that I'm placing my filter here, I'm taking the mean of all those values, and I'm going to put it in the output image here. Okay, so the first row, obviously nothing happens. Then we get to the second row. Here, nothing happens again. But if we take one more step, you can see, hopefully, it might be more visible in your own screens. Here, you can vaguely see it. There's a 1/9 value here now, because it's this value multiplied by and 8 other zeros, and you take the average. Okay. And if you go forward, now you get 2/9, 3/9, these 3 values, and 6 zeros. You take the average here. Okay? So you can just keep doing that. And you can see the output image appearing pixel by pixel. Did that make sense to everyone? Okay, so that's a mean filter. And yes?
If I don't have the slider, there's something missing in my notebook, probably.
Oh, yes.
Did we let the widgets aren't installed like expert look?
Sure. I mean, maybe we can do that later, but yeah. So the key to filtering lies in your kernel, right? So this is a mean kernel, and then there's a whole bunch of other kernels, which we're going to look at now. So to work with, we'll start with a more pixelated image because it's easier to see. When you can see the pixels, it's easier to see what's going on. So all I'm doing is I'm taking the camera image, which we briefly looked at in the first thing, and we're taking every 10th pixel, and that's what that looks like. And again, don't worry about this function. All I'm doing is plot. It's a function to plot lots of images side by side, which will be useful later. So run that cell, but don't worry about it right now. Okay, and so if we take the mean kernel of the image, then you can see pixelated, and you can see that it just blurs the image uniformly. So that's the original. Let's look at some other common filters. The first one is Gaussian, which is kind of like what we were doing before. It's an average of neighboring pixels, but it's weighted. So the pixel that you're on counts the most, and then using a bell curve that fades away, we sum the neighboring pixels weighted by that kernel. So pixels that are closer together contribute more to the average than pixels that are far away. And this makes sense from a signal processing perspective. So if you look at the square, for example, you now have slightly less distortion. It looks more, the output looks more like the original square than the diamond that we get with the mean filter. And with the camera image, the advantages of the Gaussian filter will be even clearer. Okay, so if we look at a big filter on the original image, we're doing so a 61 size filter. And then we're going to do a mean filtering and a Gaussian filtering of the same image with the same size kernel. Okay? And so you can see that the mean image has these banding. Again, it's probably better on your monitor. And that has to do with far away shifts in brightness as you're moving along, influencing the value of that pixel. With the Gaussian, you don't see that because those values are suitably weighted down. Okay? And finally, we're going to have a quick look at edge filtering. This is so we've done these smoothing filters. Edges try to detect changes in the values of the image. Okay? So we'll go back to our step signal, which we saw before. And now, instead of doing 1/3, 1/3, 1/3, we're just doing this, right? 1, 0, -1. So what this means is if I'm at this pixel, if the 2 pixels next to me have the same value, then I just get, and that value is A, then I get A minus A, and that gives 0. So if there's no change in the intensity as I'm moving along, then the filter outputs 0. But if there's a big change, then the filter will output a big value. Okay? So here's in blue, that's my original step signal. And in red is the output of the step filter. So at the 2 pixels where the neighbors are changed, which is just before the change and just after the change, you've got a very high value of the edge filter. Now, if we want to do the same thing with the noisy filter, with the noisy signal, then it's a lot less clear. You can still see it, but it's, the peak is a lot less clear than in the original, right? So here it's a very clear peak. So one thing that you can do is do smoothing and then do the edge filtering. And the cool thing is that the convolution is commutative, which means you can smooth your difference filter instead of smoothing your image, and then convolve the image well, in this case, the signal with that smooth difference filter. So here's what I'm doing. I've got this difference filter. I want to make it a bit wider so that I can fit the output of the convolution. And you can see that you get this thing where I'm taking the average of two values next to me, and I'm taking the average of two values on the other side, and then I'm subtracting one from the other. Okay? And so if we do that on the other filter, then this peak now sticks out a bit more. So yeah, that's a cool feature about filtering. And very briefly, you can now do these difference filters in 2D. So here, again, I'm doing this sold, and this is probably not what I want to do, but I don't have time to fix it. So here's our, what should have been our vertical or horizontal gradients, but instead it looks like a whole bunch of white and black noise. Can anyone guess why it's noisy? Has to do with something we saw earlier. Yeah, that's right. So the image is uint8, and so we're getting underflow. Right, if you take a uint8 and you add 1 to it, let's go above. So yeah, that's what I'm doing. Yeah? Why? I still have your keyboard, so I'm going to type slowly. All right. So you get a 0. So the values wrap around when you're doing uint8. And so here what you really want is the image as float that we saw earlier. And I think we mentioned that it was a good thing to convert your images to float, and this is exactly why. Okay, so from Scikit-image. Okay. No? What's happening? Oh, I need to recompute this thing. Right, sorry. So let's go to pixel, let's say here. And now my notebook's a big mess, but we'll forget about that. Okay, and now if hopefully this should work. Okay, great. So now we have these filter outputs, and what you're seeing is gray means 0, and then wherever there's black, it means I'm going from bright to dark, and then wherever, sorry, here, and then wherever there's white, I'm going from dark to light, okay? And same in this direction. All right, so that's the output of a difference filter. And there's a bunch of other filters. We're not going to do the exercises, such as the Sobel filter that do a bit of smoothing in addition to finding the edges, okay? So these are all in Scikit-image.filters, and we definitely encourage you to explore the documentation for those. But for now, I'll just show you the output. If you have a square and you do a Sobel filtering of that, you get the edges of the square like this, okay? So I'm going to skip this because we need to move on to segmentation. We're going to be putting solutions to these notebooks on the web after this. So go back to the sections and click on segmentation. So right now you've got all you need in terms of filtering to do a decent segmentation, which is I want to find the edges of my image. Okay, so we'll see how we use that to then find the objects in the image. So always do your map filter bin line at the start. So for those of you that don't know it, this is what segmentation looks like. This is from the Terminator. So if you've seen it, you've seen segmentation. It's just dividing an image into objects, okay? And so here, the object is that person, and everything else is the background. So again, let's set the color maps and the interpolation to none. And let's use our data and our filters to get some edges. All right. So I'm getting the coins data, which I briefly showed in the first demo, and then I'm running the Sobel filter, which I just showed before, to find the edges. So here's what the edge map of that coins looks like. I'll also show the image itself. And I don't actually need to set the CMap. Wait, why is that not working? Oh, sorry. Okay, so that's my original image, and that's the Sobel filter output of that image. So you can see that it's finding the edges around the coins in the original image. So there's a thing called the watershed algorithm, which you can find in Scikit-image .morphology. And what it does is it envisions this edge map as if it was a topographical map, and then it starts flooding from the bottom. And so wherever two different flood basins meet, that's where it places an edge between regions. So we'll try to illustrate that with one dimension. This is our one-dimensional array, which has values 1, 0, 1, 2, and so on. And we're going to put a little flood basin at everywhere there's a 0. So 1 here, and 1 here. And if I do the watershed, then it gives me 3 numbered regions where the basins meet. So Stefan wrote a nice visualization for this. So here's our array values plotted as a line. And you can see that the watershed found this region by flooding up to here. And then the peak, it's kind of arbitrary which side of the watershed it ends up on. So in this case, it ended up here. And this is our last region here. So hopefully that made sense. So we can actually do the same thing for a 2D image. No. So the local minima we had to find manually, which we'll do later. What it's trying to do is it's trying to find regions that are separated by high-valued edges. Okay, so the local minima are these red dots, and then it starts flooding up until they meet. Let's try to do the same thing for the coins image. So the first thing that we need to do is find some seeds, some flood points. And the way that we're going to do that is we're going to find things that are far away from the edges, which should be values where there's basically not a lot of rough terrain, in a sense. So the first thing we do, we use a thresholding algorithm, which tells us which values are foreground and background in the edge map. And then we're going to take all of the values that are below that threshold. Yes. And we're going to convert that into a distance map. So we're going to use the distance transform, which is part of SciPy.ndImage. So the distance map is, if I put myself at this pixel, the value at this pixel should be the distance to the closest 0-valued pixel. Okay? You're going to see that in 1 second. So if you use the distance transform, it'll leave zeros as zeros, and everything else will be replaced by the distance to the nearest 0. Okay, so all of these values are 0 here. Let me just add a color bar so you could see what the values are. Okay, so for example, this position here corresponds to the brightest part of the color map. It takes 40 pixels to go from here to the nearest edge, which is probably somewhere like here. Okay, and same here. So these are sort of in the middle. So this is 25 pixels away from the nearest edge. And then we can use this function from the feature module in Scikit-image called peak local max, which will find locations here that are peaks. Okay, and it will report back the coordinates of those pixels. So if I run this function on the distance map, I get 83 points that are two-dimensional points. So they're row column coordinates into my array. And I can draw these, yes. I'm not sure I need this beats image. Yeah, these are two separate things, sorry. So let me just split this thing. And we'll put it cell down. So I think this should work. All right. So now I'm going to show the edge map and then the peaks where the peak local max algorithm found them. Okay, so you can see that, I'll just point here, everywhere that's far away from the nearest edge, you've got a point. Okay, so you've got 2 points here, presumably because there's a bit of edginess somewhere in the middle here, and so on. So some coins have 2 peaks, some coins have more, and some coins have 1, and this one doesn't have any, which, as we'll see, becomes a problem later on.
So that was run on the distance map?
Yes. So Watershed expects, as one of the inputs, labeled numbers for the basins. So if you have, every time that you have one flood point, you should be like 1, then you've got the next one, there should be a pixel labeled 2 there. So one way to do that is to make a Boolean image, which just has true and false as its values. For every position of in that image, I'm just going to set true whenever there's a seed for every position, seed position that I've got. And then I'm going to use the label algorithm from NDimage to give me labeled connected values of true. Okay. So for all of these, there's really good documentation online, so you can go back and see exactly what they're doing.
So is the image you're going to get out is like a black image essentially, and it will be 0, 1.
Yeah, let me just display those 2 images actually. So escape. So if I am show the Boolean one. Yeah. So it's just a white spot everywhere that I had a peak identified in that original image. And then if I then show the seeds, which are the output of labeling that image, and I'm going to set the color map to be Viridis because otherwise you're not going to see anything. Even with Viridis you might see nothing. Actually, I'll do Magma. Okay, so because of the way Magma works, can you see anything on the projector? I'm hoping you can run this. Yeah, I'm hoping this is a bit clearer on your screens, but essentially you see brighter and brighter values here towards the bottom. That's just because they're higher seed numbers. Right, so this value here will be 83. Let's just do a color bar. Oh, 72. So yeah, down here you'll have values 72, and up towards the start you'll see values that are close to 0. Okay, and so now with the edge map that we started with and the seeds, we can do a watershed in 2 dimensions. And we can then show the output of that using this label to RGB function that's in Scikit-image. So here's what's happened. You've got all of the seed points, which were at random positions here in the image, And the watershed algorithm has flooded them until it found the position of highest edginess in between two flood basins. So you see some flood basins are big, some small, and some coins are perfectly contained, just one flood basin, which is kind of what we want, but some of them are split into a bunch of different smaller fragments. So what we want to do now is, yes?
So there was one coin that none of the,
Yeah, it was up here.
but I don't see it properly.
You don't, because the color map is a bit fuzzy, but it's actually like this region's yellow and this region's yellow.
Oh, I see. So the
Yeah.
fact that it doesn't have its own separate colors is because it doesn't recognize.
That's right, exactly. So essentially, if you're flooding something and there's nothing to push back, then it's just going to keep flooding into the coin. Yeah. Okay. So as I said, it's pretty good. Some of them are perfectly segmented, but some of them are kind of broken. And so what we want to do is we want to start merging them. And there's an algorithm called, what's it called? Mean boundary agglomeration, which basically looks at regions, and then it looks at the mean value of the boundary between them. And if that value is low, then it'll merge those two regions. And the advantage of that is that as you start merging more and more, then those boundaries become longer and longer, and the average becomes a better measure of the real intensity between those two things. So the bad news is that this is in Scikit-image master, not in 0.12. But that's okay, because Python's very powerful, and we can just patch the 0.12 version to include this feature. Okay, so that's what we're going to do here. So the graph, oh, I should mention. So the way that this works, do we have a pen? Yes. I don't know if any of you were at the network stuff, the network tutorial yesterday, but this is related, right? So if you have two regions, let's do 4 regions. What a region boundary graph is, region adjacency graph is, you put a node in each of the regions, and then if 2 regions are touching, then you put an edge, okay? Like this, like this, like this, like this. So that's a simple region adjacency graph. And then, depending on the algorithm, you'll put different values and things on the edge. So in the mean boundary agglomeration, we're going to go along all of these pixels, and we're going to compute the mean value along those pixels, okay? And then let's just say it's 0.3, so then you put a 0.3 value here. All right? And we can give other values to other things. So 0.8. So now, let's just go here, and we'll give this 0.4. So suppose, and one more value, sorry, 0.1 here. So suppose then I decide I'm going to merge these two things because that edge is very weak. So I'm actually getting rid of this, here's an eraser, getting rid of this boundary, getting rid of this edge, and then I am going to put one new node here and one node here. Sorry, like that. All right? And so the value of this edge now needs to be recomputed because that edge didn't exist before, obviously. And so what we're going to do is we're going to do the weighted mean of this and this. So this is a slightly longer boundary, so it should count for more. So you end up, what you really want is the mean of all of these pixels, right? And so if this was like 10 pixels and this was 5 pixels, then you would end up with 0.3 times 5 plus 0.4 thanks, times 10 divided by 15. Okay? And I'm not going to do that. And then you just keep repeating this until you have, until all of your edges have high values, basically. So hopefully that made some sense of why you would want to do that. So I'm not going to go with this function because it's very complicated, but this is kind of some machinery to merge nodes and edges in that graph, which we are adding to Scikit-image. So run that. And so then we're going to build a graph that from our watershed and our edge map that will contain the mean boundary on each edge. So again, this is in the scikit-image.future/graph. So G is rag boundary. And so let's look at what that looks like. This is this is segment number 45, so it's the 45th basin, and that's what that looks like, is this coin. And when you look at the graph and you look at the 45th node, it shows you all of its edges. So it's got an edge with a node numbered 56. That edge has 50 pixels, and the mean edge value is 0.36. Okay, it has an edge with node 9. That's a 107 pixel edge, and the mean is 0.33, and so on. So all of these are actually quite high value edge values, which you expect since this is one of those coins where it found the coin perfectly. We can look at a different one. So this is half a coin. And you can see that it has an edge with node 9. That's the same node that this one has, so it's a clue that it's an exterior node. And that's a pretty high valued edge. But then it's got an edge with node 129, and that's weight is 0.88. So 0.088. So you can see it's a much lower value. And similarly, probably another node internal to the coin at weight 0.06. Okay, so this is our graph. It's got nodes and edges. And we can do a merge hierarchical. We can merge this in a hierarchical fashion, so one pair of node after the others. And knowing how to do this kind of requires a bit of knowledge of how the internals work, but let me show you. There's clues in the API about how to do this. So this is definitely getting into like slightly more advanced Scikit-image stuff. So this is merge hierarchical, and what you want to do is you want to give it two functions. One is what do we do to the new node once we make a new node? Once we merge two nodes and we get a new one, what do you want to do with that? Or how do you make a new node? And how do you update all of the edges that get merged, right? So here we merged this edge, and we took that weighted mean. So you have to specify that using the weight func here, okay? And so here we just do exactly that. We take the weighted average. So if we're merging node source into node dist, and its neighbor, the neighbor we're currently considering is n, then we're going to get the count for each of those two nodes, each of those two edges, and we're going to get the weight, and then we're just going to get the count. The total count will be the total number of new pixels, and the total weight will be the weighted sum of those two averages. So that's this bit here. And then we just return a dictionary of those two attributes. And to do the nodes, we actually don't care what's on the nodes, so we just do nothing. So that's what this function will do. And so now we can just use this merge hierarchical function on the watershed and the graph. We give it a threshold, so that's when to stop merging. Normally, you would have to fiddle for a bit to find the right threshold for your values. But here I've done that for you. So that's the threshold where we're going to get a good segmentation. And again, to merge nodes, we do nothing. To merge edges, we pass this weighted average that I said earlier. Okay, and so the result is a segmented image, which we can look at. And that's what the boundary is. So you can see that it's given perfect results minus the bit where it could do nothing about it because that didn't exist as a watershed earlier. So In segmentation, you rarely get perfect results. This is kind of like an easy image to segment, but mean boundary does pretty good. So you can get good results with it, depending on what you're doing. So we've got about 12 minutes left before a long break. So what I would like you to do is to try to find ways of fixing the segmentation and fixing that final coin that we're missing. So the problem was that we didn't have enough initial regions to begin with. Otherwise, the region agglomeration was working pretty well. So here's two ways that you can try to fix that, or you may come up with your own. One is to do a Gaussian smoothing on the coins. So you can find essentially the center of each coin using peak local max, and then concatenate those seeds with your original seeds, and that will hopefully give you an extra seed in that coin. Or you can have a look at different initial segmentation algorithms. So if you go to from Scikit-image import segmentation, there's a bunch of functions there. You can examine how they work, and then you can merge that with the watershed using joint segmentations. So that gives you a finer segmentation than either of the starting segmentations that you did. So again, yes?
So in the box above, you set the threshold to 0.155.
Yeah.
Can you comment any more on stopping conditions for merge algorithms?
I can, but I'll have to think about it. So one way to do this a little less ad hoc than I have is to plot a distribution of your weight edges. And so then you can see if some of them are clearly like background edges and foreground edges, and try to set the threshold somewhere in the middle. But normally in all of the work that I've done, we segment a huge range of thresholds and examine the segmentations until we find the one that is closest to what we want. Also, if you're segmenting a large collection of images, you can manually segment a bunch of them. Kind of like cross-validation for machine learning. You segment a bunch of them. You then segment them manually, so you've got ground truth. Then you segment with a whole bunch of thresholds, and then you see which threshold on average gives you the best result for your training images, and then you use that threshold for the rest of the images. So that's another, yeah. It's a big field. Okay. Yeah, so try out a few of these functions that we write down and see if you can get that final coin segmented, and use your stickies. So yellow means working, etc.
Just give it.
Yeah, that's a good plan.
And we'll also kill.
And try to solve it.
What's that?
Try to solve it. I mean, it's going to be you now, right? So it's,
Yeah. I need to work the lock.
are you going to change your password now? You should at least watch the YouTube and see if it's.
If it's repeating.
That's what I'm saying.
So if you're somewhat new to the Jupyter Notebook, when you're trying to use a function, if you don't know what parameters to provide, you just type the Shift Tab together. So Shift Tab pops up a little dialog box that shows you the parameters. You type it once, gives you a small one. Type it twice, you get a bigger one. If you type it 3 times, it will pop out and show you the whole doc string. Shift Tab. Okay, so where is it here? Okay, so I was trying to solve one's challenge. We got close. So we import filters, and the filters module has got this method called Gaussian, so that gives you a Gaussian filter. I chose a sigma of 5, so that's like the width of the Gaussian with which you blur the image. The more the sigma, the higher the blur. So if I make it 1, that's close to the original, 2 much more blurred, 5 even more. So you can see how it comes out. Then I just copied from earlier on in the notebook the peak detector, and you can see it finds a whole bunch of peaks inside that smooth image. Because we blur out the edges, those peaks don't lie on the edges, so that's good. They're almost all inside of the coins, which is exactly what we want. So then I just combined those peaks that I found with the original peaks that he had found. So that's now we have the entire collection. And then I did watershed. I could just use one set, but I wanted some peaks on the outside of the coins as well, and my new ones were all on the inside, so I wanted to make sure I've got them on both ends. So then we run watershed on that, and that's the new result. And you can see, so it looks a bit misleading here because this looks like it's also purple, but this is actually an entirely new region. So these things are fine. The problem that we have is over here, where the outside of that coin is actually part of the background. So we won't be able to get that coin out still, but the rest of them look pretty good. And we may be able to fix that by using a different edge detection algorithm, to get a stronger edge out on the side of that coin.
Yeah, so that's what, sorry, what's your name? Brian. Yeah, so that's what Brian did. By changing the original smoothing, he found a stronger edge in the, right?
I added a smoothing stuff that wasn't.
Oh, there was no smoothing at all before, right? So when you did at the very start, we did Sobel. You add a smoothing step at the start, and that gives you a stronger edge.
Okay, so here where we compute the edges, he did a filter on the coins. It said filters.Gaussian, I presume,
Yeah.
and a sigma of 2.
Yeah.
Okay, you see you get a stronger edge than on the end of the coin. And if you then repeat the whole experiment, well, even our original one might work better now. I have to see what happens there.
Yeah, there it is. It was there.
If this were Photoshop,
There you go.
command called thresholds.
Yes.
That you can use to make the brighter things brighter, the bright things brighter, and the dark things darker, and then kind of stretch out.
Oh, the threshold.
So I don't know
Which-
how exactly
this one?
the Photoshop threshold works. But
What does that have to
linear
be?
transform, it makes no difference, right? But if it's,
I don't know how it works either. All I know is that if you use this to
yeah, but sometimes it's only a visible effect. So it needs to be a
Oh, yeah.
nonlinear. It needs to be a nonlinear transformation, and then you might actually get some.
Yeah, if you told it,
It's close.
if you told it a value that's in between the brightness of that coin and the brightness of the background,
Yes.
then it could enhance
Yeah.
that edge.
So doing that initial blur and then getting the edges,
Gives you.
you have to change the graph merge threshold a little bit, but it works perfectly.
Cool. Yeah, so there's lots of ways that you can do segmentation. We've just seen 2, 3. So there's a whole module in Scikit-image that you can explore for it. Yes?
So what is segmentation? What is the output? The segmentation dot mark.
Oh, so sorry. Yeah, that's good to ask. I should step on the microphone. Yeah. And then we've got a break until 3:50. but for those that want to hear the answer. So the output of segmentation is an image where every region gets a different number. Okay, so this will be 1, 2, 3, 4, and so on. So it's an integer image, and every region has its own label. Segmentation mark boundaries takes that output and puts boundaries in an image, so you can look at it. All right, if there's no more questions, then 13-minute break, and we'll start again at 3:50.
So, what's that? Yeah. So, I haven't showed you much of the Scikit-image website yet. You've seen a couple of links to the API documentation so far. So, let's take a quick look at that. So, if you go to scikit-image.org, that's the Scikit-image website, and you'll see a link at the top called documentation. And if you go to the documentation, there are two important things here. The first is the API reference, the application programming interface reference. That's like a list essentially of all the classes and functions implemented in Scikit-image. So if you click on that, you'll get a long list of all the things we've worked on so far. That's great when you know what you want to use and when you want to know how to use it. Not so great for discovering the features available. So for that, you might want to go to the gallery at the top. And the gallery is a much more graphical representation of what you can expect. So we've got tons of little examples. They're grouped. And if you click on any single example, you will get a summary and some code. And that code you can copy and paste just like that into your notebook. So you should be able to just select any snippet and go back to your notebook, paste it in, and it should just work. If that's not the case, it's a bug and you're welcome to file it. So yeah, browse through the gallery, gives you a good feeling of what's available. The other important document is if you again click on documentation, you'll see there's a user guide. And the user guide discusses many of these things that we spoke about earlier today, like how do you handle data types? What are the different dimensions that you can expect a Scikit-image image to have? How do you handle it when your images are time series, multiple images taken over time? What shape should they have, that sort of thing. So we try and answer all those questions in the user guide. And if you have a question that's not listed there, you are very welcome to ask us to add it. Right, so that's the website. The other way you can discover how things work is we've gone to a lot of effort to document the functions inside of Scikit-image, the same way we've done with NumPy and SciPy. So if there's any function that you don't know how to use, so let's say we saw the filters from Scikit-image import filters, and you saw earlier on the filters.Gaussian function. So if you type, like I said, open the bracket like you're going to use the function, and then type Shift-Tab 3 or 4 times in IPython, and it will pop up this doc string. Now, this is the same doc string that you will find in the API reference, but it's handy to have it inside of your notebook. And you see that for each function, we document the parameters, so the input parameters. We define the returns and their data types, and sometimes you get a couple of implementation notes if you want to know design decisions we made while we implemented the functions. Typically, we include a couple of examples too, and for some functions, you'll find references to the papers we implemented as well. Okay. So this section is going to be about RANSAC, the random sample consensus. Like Wikipedia says, it's an iterative method that helps you to estimate parameters of some mathematical model from a set of observed data which contains outliers. So you can also think of it as an outlier detection method. Big words, what does this mean? Let's have a look. So we're going to do our standard import NumPy, import matplotlib, and then from skimage.measure, we're going to import RANSAC. To illustrate to you how it works, I'm just going to generate some data So you can examine the cell later on, but all it does is produces this data that you see plotted over here. So it starts with a straight line. It generates points on that line, points a little bit off of that line, points sort of scattered all over the place, and then in the one corner we've got a little cloud of points lying over there. So the challenge I want to set myself here is fit a line to this data. And if I asked you to solve that problem, you would have told me immediately, just looking at this data, you would have said, well, it's obvious where the line should go. The line runs down there. But if you ask a computer to solve the same problem, it's not that obvious. So how would you typically do that? Well, let's take a look. So we start with our model of what a line is. There are various ways of parameterizing a line. We're going to go with the traditional y equals mx plus c. Do you know why that's a really bad way of representing a line? What happens when the line is vertical? Yeah, so m has some degenerate values. But let's not worry about that for now. Let's say all our lines are well behaved. That's our model. And I'm going to represent it in matrix form. So I can say that for a bunch of x coordinates, my y coordinates are equal to x times m, mx, plus c. So this is just a column of ones. So this is the matrix form of what I wrote over there. Now we know how to solve matrix problems. In this case, we have many more data points than what we have parameters to our line. How many parameters does this line have? 2. It's got m, the gradient, and c, the offset, or the intercept. So we're trying to solve 2 parameters. We've got hundreds of data points. So we can't do a normal solve. So we're going to do a least square solution. And NumPy has got linalg.least squares that allows you to do that. So I pack my x coordinates and my y coordinates into a vector. I construct this x1 matrix by taking all my x's and putting a bunch of ones next to them. And then I do the least squares solve. So I solve for MC given my x coordinates and my y coordinates. Okay. So if you have some background in linear algebra, or if you've done an introductory course, this would make sense. If not, this is just a standard way of doing a least squares fit of a line through all that data. And there you get your gradient and your offset. And with the parameters, we can just plot the lines. You'd see I compute mx plus c. And what do we get? So there's the line. So you see that we've got a bit of a problem here. The line is not a very good fit. And why isn't it a very good fit? Well, it's mostly due to these points over here. These points are kind of scattered all around our line. So as much as they pull the line up, they pull the line down, and the effect kind of cancels out. But this group of outliers over here, they're very problematic because they skew the whole line fit down. And we don't want that. So before we go any further, I just want to show you that Scikit-image has a line model that can do exactly this kind of fit already. So, and it simplifies the notation a little bit. So I'm just going to take this brief detour and show you that. So from skimage.measure, like I said, we import ransack, but I'm also going to import our n-dimensional line model. And the line model, all that I did above can be repeated in these 3 steps. So construct the line model, estimate the line model from the data, and then finally grab your parameters out. And you can see that that line has got different parameters because we don't use the bad parameterization. And instead, it gives you an origin and a direction. So that's the new way in which we visualize the line. We say the line starts somewhere and it's got a direction. That's a much better way of parameterizing a line. But if you do the plot of the line by doing model predict y values from x values, then, oops, I should run that. Then you see that we end up with the same thing. So I just want to show you that the line model in Scikit-image does the same as the least squares fit. Okay, so we're at the same problematic point. Where can we go next? Well, this is where ransack comes in. So ransack is quite a clever algorithm. And the way it works is as follows. How many points do you need in order to fit a line? How many data points? 2. If you have 1, the line can sit through that, but it can vary in angle. If you have 2, the line is perfectly fixed. So what ransack says is, let's go ahead. Let's pick any 2 data points randomly. So just pick one there and pick one there. And I fit a line through it. Boom. Okay, so that's my first model. And then what I go and do is I say, okay, there's the line running through my data. Count the number of data points that lie close to that line. And I see, okay, there's a bunch over here and a bunch over there. So maybe 50 data points. And then I say, okay, let's repeat that procedure a few times. So I grab another 2 data points at random, fit a line through that. Okay, I get 30 points of my data that lie close to that line. And I keep repeating that process until eventually, by sort of luck, I pick a point here and a point there. The line runs over like that. It runs across this dark blue line. And when I start counting the inliers, I suddenly see like, boom, I've got 400 inliers. So you repeat that procedure several times, and there's a statistical way of knowing when to stop. But you just repeat it a bunch of times, you count the inliers, and at the end you say, okay, so now I'm going to take the model that had the most inliers, and that will be my official model. Well, you'll then throw out all the points that you think are outliers, do a final fit of your model, and that will be it. Is that concept clear to everyone? Does that make sense? Or is there's something? Yeah, go ahead.
I assume we have to give it some idea of what we mean by close.
Absolutely. So that's a good point. Ransack has to know what is considered as an inlier or an outlier. What is close to my model or what isn't. So we typically give it a threshold and say, like, if the line, so I pick my 2 points, I fit the line, anything that lies, say, within 5 pixels of that line, I consider to be an inlier, everything else an outlier. Any other questions?
So it usually uses pixel distance?
Yeah, so we usually use pixel distance, but you can define the model to be anything you want, and the model gets to evaluate, what is an inlier and an outlier. So you can do anything that you want to. All right, so let's move forward with that idea in head, and let me clear this out because it's spoiling all the fun. Okay. So right, so that was our least squares fit. So now we're going to do a robust fit using ransack. And the way we do that is we call ransack, that we just imported from Scikit-image. We tell it, do this fit on our data, use the line model, the n-dimensional line model, use a minimum number of samples of 2, so always pick 2 points at random from our data set. Take a residual threshold of 10, so anything within 10 pixels we consider to be an inlier on that model, and don't repeat the procedure more than 1,000 times. And that's it, and then you execute that. It returns the new model that it estimated, so that's your robustly fitted line, and it returns inliers. Inliers is just an array that says true, false, true, false, 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 true, false, corresponding to the number of data points you had. So it says for each data point, are you in or are you out? And then we can do what we did before, just plot the line according to that new model, and let's see what we get. So there we go. I also colored the outliers red and the inliers blue, so you can see that these points were rejected, those points were all rejected, and only points 10 pixels within the optimal line were considered to be inliers. That's exactly what we wanted. All right, so I'm going to give you a chance to practice ransack. And what we're going to do is we're going to analyze an image of the sun. So the sun apparently is one of the roundest objects in our vicinity. So if you take a photo of the sun, a 2D slice of the sun, we imagine that you should be able to fit a circle to it perfectly. So instead of a line model, we're going to be using a circle model that Scikit-image already includes for you. And so we're going to start off by loading this image. And what I want you to do is take this image, compute its edges. If you compute the edges, you'll find a bunch of edges lying here on the outside, and of course a bunch of cruft on the inside. So if you just did a least squares fit of a circle on that, you would have a problem, because the circle, I mean, where would it go? It wouldn't know where to go. So get the edges, find their coordinates, and then use ransack to fit that circle model around the sun. All right. I gave you sort of a template to work from, so just go to the notebook and start modifying that code. Sticky notes, if you could put on the yellow sticky notes while you're busy, and the red ones if you run into problems, the blue/green ones if you have success. And if you manage to complete this exercise really quickly, there's another exercise where I ask you to find the edges to identify a credit card inside of an image. So this was part of the next lecture, but since we're joking about the topic right now, I thought I could show you quickly. This is an example I was going to show you just now. It's a swirled face of the Mona Lisa, but there was this criminal in the UK who committed some felony, and every time he did the crime, he would post to the police about this on a bulletin board using his face twirled up like that. And the police knew some people who could do some image processing, so they managed to unswirl his face, identify him, and they went and arrested him. So we'll play around with that in the next section. Yeah, I'm sorry if I spoiled it for you. So technically we have a break starting in about 2 minutes, and you're welcome to take the break or to keep on working. I will do the solution in about 7 minutes from now. Okay. Great. So let's look at that solution quickly. So I guess you must have all noticed that we've got the solutions in that repository as well. So if you go to lectures, solutions, and you will find them all there. And currently we're looking at ransack. So there's the sun. I used the canny edge detector with sigma of 2 to get the outline of the sun plus some squigglies on the inside. There's a nice little ejection on the side of the sun. We use the circle model from Scikit-image. We get the coordinates of all the edge points. That's our data. And then we call ransack on those coordinates with a circle model. We say take a minimum number of samples, 3. That's what you need to fit the circle. I took a very close threshold to make sure the inliers lie very close to that circle. And I used max trials of 5,000, because if I use 1,000, I found that sometimes since it's random sample consensus, it sometimes fitted the wrong model. But when you do that, it's pretty robust. It almost always works. Well, I haven't seen it fail yet. There are the parameters. And there you go. You know, I look at this example and I just think, like, this is actually a fairly impressive result. It's like you start off with an image that, of course, easy for a human to look at it, but even for a human, it's kind of, where is the edge of the sun exactly? It's not that easy to define. And with traditional approaches, this would have been a really hard problem to address. And here we go. Here I identified the inlying edges all on the outside, the greens on here, and the model fits the sun perfectly. I'll just quickly show you the solution to the card shark example as well. So we read the credit card in, and then I have this simple for loop. So all it does is, it grabs the edges of the credit card. It grabs the coordinates. And then what I do is I fit the line model to my coordinates. So that should give me one of these edges of the credit card. Then I remove all the points that lie close to that model. So now you have like the entire credit card except for the one edge. And then I repeat that procedure. And I do it 4 times. So each time you remove the inliers and you fit on whatever remains. So you can see, fit the model using Ransack, plot the resulting line, and then say take the edges and remove everything that's not an inlier. And that just repeat that 4 times. And when you execute that, there you go. So in this case, didn't work. Let's try again. So if you up the number of samples, you're probably in a better position. Yeah. It is random. But if you do it enough times, then you're likely to get the right thing. And of course, this is just sort of to show you how this works, right? You could always afterwards go and check your result. You can like say, is the region I found in the middle, is that a square thing or is that a rectangular thing? If it's not, I probably didn't find a credit card. And you can repeat the process or try some other algorithm or whatever. All right. Any questions about this section or any of the previous sections? Anything that came up? Any questions? Yeah, go ahead.
Can I just see the solution?
Of course.
Problem again?
Yeah.
So when you're finding the first line, it's just finding the most abrupt line?
So it's finding the line with the most inliers. So we've got the 4 edges of the credit card, and it basically picks 2 random points, right? And then it fits a line through that. So eventually it's going to pick 2 random points on one of the lines. Now, those lines, the 2 sides of the credit card have almost the same number of edge pixels, but the one will still have slightly more than the other. So you always have a first line that gets picked. And then when you remove those outliers, it will then get the second and the third. So it will take the 2 longest edges first, and then the 2 side edges.
So if this is like complex, but if you wanted to say, only pick lines that have some kind of length or some other characteristic, is there a straightforward way to?
So is there a way to say, to pick only lines that match certain criteria? Well, I'm not going to go into how the models are structured, but if you just look at the source code for line model ND or for circle model, you'll see that there's a function that gets called each time that decides what is an inlier, what isn't, and there's another one that gets called to see is the data I selected valid. So by using those 2 things in combination, you can reject anything that doesn't work for you. And of course, you can also post-process your results. So yeah, various approaches to doing that.
So is there a rule of thumb of when to filter?
Of when to filter?
Yeah, and when not to filter before you do extra?
Is there a rule of thumb of when to filter and when not to filter? So I think that would depend a lot on the nature of your input images. If you have very noisy inputs, or if your input is badly behaved in some way, then you probably want to clean it up beforehand. The best way by far in image processing to improve results is to improve your acquisition itself. So much work and research has been done on, like my PhD thesis was on super resolution imaging, but you could just mount a better lens on your camera, right? And Sometimes you can't, like if you're out in space or if your Mars rover has already been launched 10 years in the past, then sure you can't. But in most cases, I would spend the extra few $1,000s on the hardware and get better results out. Make sure your lighting sources are adequate, make sure all those things are in place. But yeah, so you try and clean up the image with pre-processing a little bit as much as you can. And as soon as you've got results where the algorithms can fairly robustly determine the output, then you're good to go. But it's one of the slightly annoying things about image processing. There are a lot of heuristics involved. And I think one of the most exciting new directions that we see being followed is this combination of sort of parameter learning, like machine learning combined with image processing. One mentioned a little bit earlier, one of those approaches where you sort of, you can do a few segmentations by hand, learn the parameters, and then apply them to other data sets. And I think we're going to be moving more in that direction.
So that means then you're not going to be playing around with your arguments.
Exactly. Like you don't want to be playing around with parameters. You want parameter-free algorithms whenever you can. And I think that's one of the very appealing things about neural networks is that you just train on a bunch of data, you throw your image in there, and there's a magic output, right? Yeah.
Yeah. The network architecture.
Yeah, no, sure. There are always things you can tune, but. All right, so if you have any more questions, I'm happy to answer those. Otherwise, let's move on to the last notebook of the session today. So the where were we? So that's geometric transforms and warping. So at the top of this document, I've added a few links into the documentation. So you see, I linked to the transform module itself, which contains a whole bunch of things that we're not going to discuss today. But the two things I want to look at, I want to show you the warp function, which will take an image and transform it according to some model. So you can think, for example, the one we'll see is rotation. So take an image, you've got some geometrical model that says twist the image around, and then we've got a method of applying that. We've got a whole bunch of models. There's the affine transform, similarities, homographies, whatever you need. There's piecewise affine, there's polynomial, whole bunch of these things. We're just going to look at a very small subset of all of that. And this lecture I'm going to flip around. I'm going to have you start with the exercise, and then once you figured out the problem, that will provide us with a question to answer. Does that make sense? So what I'm going to ask you to do is take a NumPy array that is an image and write a custom function that will rotate that image by, say, 30 degrees or theta degrees. So you can start by reading in the camera image. That's just data.camera. Data is an example data set inside of Scikit-image. Let me execute this. And of course, you could use the built-in rotation method inside of Scikit-image.transform. So that's one line of code, will rotate the image for you. But that's not what I want you to do. I want you to write your own custom function. So start off with something like this. Def rotate image angle and do some stuff here and return a result. And then do plt.imshow result, and that should be a rotated image. Okay, so I'm going to give you like 15 minutes to try and sort that out, and then we'll discuss whether it's easy or hard and why. Just in case you needed a reminder of polar coordinates, which is one way of doing this, but it might be one of the easiest ways, is when you start off with a single input coordinate, let's say we call it xy, we could write that same point in polar coordinates as a certain radius and a certain angle phi. So the radius is simply x squared by y plus y squared, the square root of that. And the angle is the arctan of y over x. So you use the numpy.arctan2 function for that. So that gives you the radius from the origin and the angle. So to rotate that point, you just add your however many degrees you want to the angle. So your new coordinate becomes r and phi plus theta. And then you convert that back into xy coordinates with r cos that angle and y is r sine that angle. Any indication, who thinks that they've got a reasonable shot of getting to this within the next 5 minutes still? Who thinks this is a complete lost cause and that I should rather explain the answer? What do the rest of you think? Don't throw stuff at me. Okay, so Thomas, I'm sorry, I'm just going to move ahead then, because it seems we've reached a level of despair here that I have to put down quickly. All right, so so the thing we want to do is, so we want to rotate this image, and intuitively, the first thing we want to attempt is we want to say, well, okay, so we're going to start off with so you're going to start off with an image of, let's say, Chelsea. I don't know how to draw a cat. Okay, so there's Chelsea. You want to rotate Chelsea by 30 degrees. So what do? Well, you create a new output image. And in the new output image, you want this whole thing to have been rotated like that. So that whole image must now essentially sit like over there. So you expect to see, the cat like something like that. Okay. So how do you do that? Well, each coordinate, you go across all the coordinates in the image, and you say, here's a pixel. Where should that pixel go to? Well, there's the coordinate. It's some r phi. That's your polar coordinate. Some radius, some angle. You add 30 degrees to that angle. You convert it back to xy. So that's your new position. But you don't want the position in this image, right? You want it in the output image. You say, where should this pixel go? Well, it should go over there. It's a bad drawing, but you get the idea. Spun around, and you take that pixel value and you pop it in there. So you go across every single pixel, figure out where the pixel should go, and you pop the pixel value in there. And that's your result. But so that's exactly what I did here. I say for x in all the columns in the image, for y in all the rows in the image, calculate the polar coordinates. So calculate the r, calculate the phi, add a certain number of degrees to that, calculate the new x and y coordinates, and at that new x and y coordinate, just co-place the original image value. But when you do that, not only does it take a very long time, but it gives you this. So what's, yeah? You can go ahead. So you're running ahead of me, yeah. Yeah, but you've got the right idea. So you have this problem that when you take these pixels and you project them over there, then some of them end up in the right positions, but there are some black holes that remain in this image. You can see like lots of black dots over here that never got a pixel. And it's because when you put this one over there, two of them might fall on the same end destination, and some of these pixels might not be covered at all. So that's a problem. So Thomas has the right suggestion on how to fix that. So instead of running over the pixels of the input image, you say, let's start with the output image. And what should each value look like? Well, for each pixel here, let's see. So let's take the cat eye. So there's the pixel. Where should I get that value from? Well, that value, I can calculate the transform in reverse and figure out where that value should come from. It should come from here. So you transform it, grab the value from here, and put it in there. Go to the next pixel, do the same thing. And that way you sweep across your entire output image, and each value you go and fetch on the input side. And that way you don't get those black holes. You get the whole output image. But now there's an additional problem. Like if you transform the coordinate back to this side, will the transform coordinate be an integer? It won't. Most likely it won't. So you're going to end up in this situation. Let's just zoom in on this little part of the image. Say we're looking at the eye, and we've got 4 data values here. So this is your grid of values. Now you take this output coordinate. Here's your output image with all its pixel positions. You take your pixel and you warp it here. And you say, okay, I want the value over there from my input image. Do I know the value at that position in my image? I don't. It doesn't fall on top of any of these known pixel values. So what do? You interpolate. So interpolation is the method by which, given these 4 values, we can figure out what the value at that position should be. So you can use cubic interpolation, bilinear interpolation. There are lots of different interpolation methods. The easiest one is probably nearest neighbor interpolation. You say, just take the nearest pixel value to that position. It gives kind of crummy results. Your output image is very blocky. It doesn't look very good. So a much better way of doing it is saying, well, we want to know what the value is at that position. We can't figure that out from this. So let's start by simplifying the problem. Let's first figure out what the values are at these 2 positions. That's not too hard to compute. I can say, like, just weigh these 2 values according to the distance from each. So if I'm closer to this one counts more. If I'm closer to this one, that one counts more. So you just linearly weigh them, and you calculate that value. Do the same on this side. Linearly weigh them, calculate that position. And now I can say, well, what should this value be? Well, I just repeat the same procedure. So you say, if I'm close to this one, weigh this one more. If I'm closer to that side, weigh that one more. And that way you can calculate a good value for that position. The reason I go through this whole exercise is because when you use the warping transformations or the warping functionality in Scikit-image, you always have to specify the reverse transformation. And people keep asking, why do I have to do this? Because I know my transformation going forward. I want to rotate 30 degrees in that direction. Why do I have to specify 30 degrees in the other direction? And that's the reason for it. It's that we need to go backward from the target image to the source image, not from the source image to the target. So once you know that, the warping functionality becomes a lot more clear.
So you now still get black boxes at the edge.
You don't.
Black corners.
You don't get black values anymore because you now sweep across your entire output image. And when you go back, you interpolate. So you can't like go back in here and then miss a value. I mean,
Oh, you can on the outside.
oh, on the outside? Yeah, of course. But
Yeah, so you do get the black borders, but you don't get black values inside.
yeah.
Yeah, just to clarify, so what you're saying is that for people that are in the back of the room, can't see, there's a bunch of little black pixels in there that are becoming,
Can you see it now?
yeah, I can see what's there. Okay.
Yeah.
It all makes sense. Thank you.
Cool. Sorry about that. Okay, so we've spoken about interpolation. So Okay, I'm going to give you 5 minutes to just play around with some warping. I gave you this fisheye example. So how does it work in Scikit-image? Well, we know we have to specify the warping function. You have to tell Scikit-image, how do I go from my output image to my input image? So the way you do that in Scikit-image is you define any function that takes an array of x, y values, and you modify those x, y values whichever way you see fit, and you return the new x, y values. That's it. That's all you need to do. Once you've done that, you simply call transform.warp, you give it your input image, and you give it your transformation function, and everything happens. Emphasis again on the reverse. The transformation function is always the inverse. So here I've given you the fisheye example. I calculate the center, the x and the y coordinates measured from the center. I convert that to polar coordinates like we just did, and then I do some computation on the r, and then I return that the new x and y values. And then you get this. So here I've given you another transformation function, a swirl function. If you run that one, kind of spins the face in. And the next challenge is like, take this template that I've put down, modify it, and do something fun with it. I just added a little sinusoidal ripple, but just mess around with it a little bit, change it around, and see if you can do some cool effect. I'll just give you 5 minutes to play around with that. You don't have to use my face if you don't enjoy looking at that. So you could just use a cat image or the camera image or whatever. So if you've managed to make a particularly good transformation, post it on Slack or send it to me via email, tweet it or something, and we can get it out there. In the interest of time, I'm going to move forward. We've got 10 minutes left, and I want to give you a quick demo of the panorama stuff. Just before we get to that, here's the final exercise that we didn't get to now, but it's an example from a church floor in England, and the challenge here is, given this photo of the church floor taken from an angle, so you know the floor is it's a plane, and you took it from some position, so you know that plane is like warped in some way. From the geometry, we know that an affine transform can correct that. And if you click on the 4 coordinates here, if you identify the 4 corner coordinates of the tiled floor, and you know you want that to go to a box, then you can compute the inverse transformation and rectify the box like this. So it's quite useful if you're, for example, trying to see the Mona Lisa or some other artwork, but people are in front of you and you can't really get there, so you're just going to take a picture, and you've got the picture, but it's all messed up and like the image is like warped. Then you can use this kind of technique to squeeze it back out into a rectangle and pretend like you were standing right in front of it. All right, so the last bit, you could just sit back, relax. I'm going to run with you at hyperwarp speed through a panorama example. And I'm not asking you to follow everything along. I just want you to sort of get the rough idea of the capability of Scikit-image in this case and of what we can do. So what we're going to try and do is we've got a bunch of pictures. Josh, one of the other Scikit-image contributors, went out into the desert specifically for this tutorial. And he collected a bunch of data. The data looks like this. So he stood in front of a rock formation, took a picture, took another picture that overlapped with the first and the third one, and now we're going to try and stitch those 3 pictures together. So how are we going to do that? Well, the first thing we want to do is we want to identify features in this image that are also present in this image. Once we've identified those features, we want to match them up. Once we've matched them up, we want to get rid of the ones that are not very good. So that we do between the first 2 images, and then we do the same thing across the second 2 images. So let's start with that. So we make the images a bit smaller because we don't want to wait so long. Convert them to black and white. And then we use a thing called orb. It's a certain kind of feature that you can extract to extract features in these images. And then there's a, oh, where are my results aren't displaying. Oh, they are. I was just being impatient. I'm sorry. So black and white pictures, we extract these orb features, oriented, rotated, brief features, which just means they're kind of a little bit invariant to rotation. And this is what we get. Okay, so you see that it found features, it matched them up. There are some pretty crazy matches over there that clearly aren't valid, but it's fine. We start off with that. We do the same between the last two images. And then, so clearly again, let's see. So that's still unfiltered, right? Yeah. So those are all bad matches. And then we use ransack, the method that you had just seen, to filter out the bad matches. So what we say is, take the input image, take the two images, figure out some model. We use the line model or the circle model. We say, figure out the transformation model that corresponds to most of the data I have. So reject some data, push them out, and figure out the model that best describes that transformation. So if we do that, we can see that these are the matches that remain. And that looks a lot better. You can do it on the second image as well, or the second and third image, and this is what you see. Okay, so much cleaned up from where we started. Okay, now we've got valid matches. So where do we go from here? Well, now we can transform the image according to the model that we matched. And we can see what we end up with. There we go. So according to those matches, I've now warped those images, and we're ready to stitch them together. So we're just going to sum them, and where they overlap, we're going to divide by 2. If all 3 of them overlap, we'll divide by 3, just making sure that the weights are correct, and we get something like this. Beautiful, our job is done, except this looks horrible. We've got edges over here due to edge effects when the interpolation happens. And if you look at the bottom of that image, it's kind of blurry. Like when we average these two images, the match wasn't perfect. So we get this soft blurriness over here. So not at all what we want. Good start, but not good enough. Okay, so what do we do next? Well, we take those two images that overlap, and we calculate the difference between them. And this very clearly shows us that there are some pixel misalignments over here, over there. You can see that you get edges because the mountain is like slightly shifted between the two images. You can see this edge coming out. So, new strategy. What are we going to do? Well, instead of blending the pictures together, we're going to take a pair of scissors. We're going to cut up the first image. We're going to cut out the second image with exactly the same pattern, and then we're going to glue them together. Where will we cut the images? Well, we look at this difference image, and we say we must find a path that does not intersect any of these big differences, because then you'll see a jagged edge in the image that you stitch together. So we're going to find a path that runs sort of through here, and then sneaks through there, comes down here, maybe around there, and sneaks through there, out there. And we're just going to cut it very carefully there, and hopefully we won't see the misalignments then. How do we do that? Well, Scikit-image provides you with minimum cost paths. So you set up your cost array, which is that difference that you just saw. And you have to be a little bit careful in how you set this thing up. So right here in the middle, you see the difference between the two images. And at the top, you'll see slightly varying gray shades. So the only reason for that is because you'll see that there's a slant over there. So you want the cost to enter from that point to be the same as the cost to go from there to there. So you make this a little bit the cost a little bit lower over there, so that by the time you reach the image, you've only gone like X cost, and that's also X cost. So the same, so it doesn't matter where you enter the image. It's just to make sure that there's no preference in where you start to cut. All right, so find the minimum cost path and display it, and voila. It says, so I was slightly off. It's not trying to sneak through there. It's actually going through there and okay. So that's where we're going to cut the first 2 pairs of images, and we're going to do the same with the second pair. There's the, whoopsie. There's the line along which we're going to cut. There's the mask for cutting. And there's the second pair of images. We're doing the same thing, figuring out where to cut. And let's compute the cut. And boom, there we have the 3 images all cut. And you can see those 3 pieces can now be fit perfectly together. So let's put them together. And voila. Perfect stitch, no border effects, no blurring, and you can't see where the images were cut because we cut very carefully in a very sneaky way. So let's do it in color, just for the fun of it. Why not? There we go. There's your big panorama. Oops, it's too small. Yep. So that's just to give you a feeling for the kind of power you have with these tools at your fingertips if you know what you're doing. Which I'm not saying I am, but yeah. Josh set this up. All right, so thank you so much for your time and attention. We appreciate you being here. If you have any questions whatsoever, feel free to ask us. We've got a Gitter channel, so we're there from time to time. The mailing list is available to you, and we accept pull requests on GitHub, and we're very happy to discuss issues with you. If you run into any difficulties using the software, come talk to us. If there are any features that you need in order to complete your work, let us know, and we'll see what we can do, or we'll work with you to implement it. Finally, grab a sticker on your way out, and I think that's it. Thank you.